Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to talk about how to solve the equations of motion for a mechanically oscillating system with no external forces acting on the system, no damping or no little person pushing on this mass or anything like that. So in my previous video I talked about how to derive the equation of motion for a mechanical system. In this case, again, we're going to look at just a standard mass spring system. We're going to assume that this mass has an equilibrium position, which I measure from this position with positive x to the right. We're going to assume it has been shifted an amount a to the left and released from rest. And I'm going to talk about how to derive or how to solve the equations of motion for the system. These are kind of important. In this example, we're going to assume at t equals 0, it starts from rest, so the velocity is 0, and it's at a location x equals minus a being whatever distance this has been shifted over. All right, it's released from rest. Second picture, at a kind of a generic time where x is somewhere between a and 0, you draw a free body, write a Newton's second law equation, or you write out an equation for the energy. Your Newton's second law equation or the time derivative of the total energy of the system will yield this equation right here, and I went through that in my previous video. Now I'm going to talk about how to solve it. Now what you need to recognize here is the mathematical format of this equation here. Remember that x is some function of time, right? And then we have time here. So time is our independent variable, x is our dependent variable. This equation is saying whatever x is, you need to be able to hit it with two time derivatives, add it to a multiple of itself, and get 0. There are only two types. There's only really one type of function in the whole universe that exhibits that behavior, and that's the trigonometric functions, right? Sines and cosines. Sines and cosines are basically the same thing, they really only differ by horizontal shifts on a graph. So what we're looking at is we're looking for some function that looks maybe like this. Maybe it's a sine wave, like maybe a C1 sine of C2t. Or maybe it's a cosine wave, so maybe C3 cosine of C4 times t. Either of these two functions will solve this type of equation, and the sum of the two will also solve it. Now, hopefully you've watched either my videos or some other videos on how to solve differential equations, but here's a fact about linear differential equations. If I have two functions like x1 and x2 that solve a given system, the sum of the two also solves it. And the sum of the two is what's called the general solution here. So the general solution of this equation looks something like this. C1 sine of C2t plus C3 cosine of C4t. Now, again, if you have seen my videos on this differential equation theory stuff, solving second order homogeneous differential equations, you will notice that these constants are the same, always end up being the same thing. And you notice that those constants have to have units of radian per second, because if you're going to take the sine of an angle, standard unit of angle in physics is the radian. So the quantity that has units of radian per second is called the angular frequency. It's usually denoted with the letter omega here. So what I'm going to do is I'm going to take this equation and I'm going to just write it as C1 sine omega t plus C, I guess I'm calling that 3 now, cosine omega t. Now, whether you call these like A, B, C, D, or C1, C2, C3, C4, that's completely irrelevant. I mean, in other videos I probably called these constants different things. The names of them don't matter. What does matter is you need to recognize that the general solution here has both sines and cosines, and it's got three possible constants to determine: the C1, the omega, and the C3. All right, so this is basically your starting point. Because I'm looking at an equation where we have to differentiate it twice, add it to itself, and get 0, sines and cosines are the type of function that's going to solve that. We don't know which yet, and the sum of the two is called the general solution. So this is our starting point, basically. Now, Sometimes you have initial conditions in problems, sometimes you don't. In this particular problem, we have initial conditions. I'm going to apply this condition first to tell me some stuff about this equation here. So at t equals 0, the velocity needs to be 0. This equation is for position, not the velocity. The velocity is given by the time derivative of this. So I'm going to go ahead and write x dot equals. Remember, x dot is the kind of shorthand notation for dx dt. If I time differentiate this, this is going to read c1 times omega times cosine omega t, because the derivative of sine is cosine. And if we differentiate this term, we're going to get minus c3 omega sine of omega t, because the derivative of cosine omega t is minus sine omega t times the omega. Now I'm going to apply the condition that at t equals 0, the velocity is 0. So this is going to read 0 equals c1 times omega times 1, because the cosine of 0 is 1, minus 0. Now this 0 is because the sine of 0 is 0. Now as we look at this equation here, either c1 is equal to 0 or the omega is equal to 0. But this guy cannot be 0. The reason is look at our solution here. If this were equal to 0, our solution would just read x equals 0, because the sine of 0 is 0, plus c3, because the cosine of 0 is 1. And that would be saying that x is constant, but that can't be the case. So the only possible solution to this that will physically work is the c1 equals 0, which means, going back to my original equation here, this term is gone. So my equation now is going to simplify to just x equals c3 cosine omega t. Next, the c3. I think what I'll do is I'll save that for last and go after the omega here, the angular frequency. To get this guy, you have to use our differential equation here. And in order to do that, we're going to need the second derivative of x. So I'm going to go ahead and get that first derivative. So let's see, minus c3 omega sine omega t. There's our first derivative of this function. Second derivative, differentiating this guy, is going to be minus c3 omega squared cosine omega t, because the derivative of sine is cosine, but when we differentiate that omega term, that's going to give us another one here. So what we're going to do now is we're going to sub this and this into our original equation. I'm going to need some room to do that. I don't think we're going to need any of this anymore. All right. So this equation is now going to read the second derivative of x with respect to time squared, and that's what I've just calculated, minus c3 omega squared cosine omega t, plus this term, k over m, times x. This was an x dot here. X, I erased it, was c3 cosine omega t is what x was. So I'm going to put that value here, c3 cosine omega t equals 0. So we glance this over. Notice that we can factor a c3 out, and we can factor a cosine omega t out, and then we're left with minus omega squared plus k over m equals 0. All right, so now we have the product of three things equals 0. This guy can't be 0 for the same reasons before. We wouldn't have a solution left. If we set c3 to 0, we just have x equals 0, and we wouldn't have a physical solution. Same argument with this. So the only acceptable solution to this is coming from this. So the angular frequency is equal to the square root of k over m. This will be some number, given we would have to know a spring constant and a mass. And this number will come out to units of radian per second. So our solution now, as I update it, is x equals c3 cosine of square root k over m times t. Now, depending on the type of problem, if we were after only the frequency of the system, we would have it. We would be done. If this was a known value, we would have the frequency, and I think I'll save that for another video, how to get the frequency of the system. The intention of this video is just how to solve the equations. We're almost done here. The last part is to get C3. We can get C3 in this example from this condition, that at t equals 0, x is equal to minus a, whatever a is. So we apply that condition. X is equal to minus a when t is equal to 0. So this thing is going to read minus a equals C3 times the cosine of 0. It doesn't matter what this is. If you put a 0 here, that whole term is 0. Cosine of 0 is 1. So C3 is equal to minus a. So we have our solution. X equals minus a cosine of root k over m times t. Now again, that's presuming we know numbers for a, k, and m. I think I'll write that so it's a little more legible. The particular computer I'm using right now is a little bit tougher to write on than some of them. Okay. So the point of this video was how to solve the differential equations of motion for a mechanical vibrating system here. And let me kind of overview how you do that. You start by writing out the general solution of the system. Now, what that looks like is going to depend on what type of variable you're using to track your system, but it will look something like maybe x equals a c1 sine omega t plus c2 cosine omega t. If you're using maybe theta to track the location of your system, this could be a theta, or maybe if you're using y, this would be a y. The little details like that don't matter. It's going to be whatever your coordinate is equals a constant times sine omega t plus a different constant cosine omega t. So the general solution of these equations always has this type of form, assuming there's no external forces acting on the system. If you have initial conditions, you apply them, or you can apply them. There's three possible things to do in this problem. We can apply that at t equals 0, the velocity is 0. You would do that by differentiating this to get the equation for the velocity and then apply that condition. In this problem, we have a position condition here at t equals 0, x is equal to a. You apply that by taking your position function here, putting zeros here, here, and putting your known value for x here. That'll nail down another constant. These guys, the angular frequency, you always have to go to your differential equation to get that. So what you do is you take what's ever left with your system. You're going to need to calculate a second derivative, and that term will go here. And then what's ever left in your solution here goes here, and you'll get the angular frequency out. I think I'll save the interpretation and how to what you do with this for another video, as this one's gotten to 13 minutes already. So I hope this video helps teach anyone watching how to solve the differential equation for a simple harmonic system. Have a great day.